Hello everyone, and welcome back. Today we're going to continue our exploration of optimization methods, but now we're going to be focusing on how we can use calculus to solve some optimization problems where the function we seek to optimize could be linear and more generally nonlinear. And derivatives and also partial derivatives are very important tools that we can use to solve those problems. So what we're going to do today is we're actually just going to focus on the single variable calculus differential applications of optimization and introduce a few scenarios for where you can actually use these in everyday life. And later on in this series, we'll talk about how we can use, for example, multivariable calculus to solve functionals that have, for example, more than one variable for which we seek to optimize over. So let's assume that you're in charge of selling donuts at a bakery with X the number of donuts that you sell in a particular day. And suppose that the revenue and cost are represented by R and C, and they're associated by these particular constraints that we typically are familiar with already. So what we want to do is we want to figure out what value of x actually maximizes the profit function. So if you don't already know how to construct a profit function from revenue and cost, keep in mind that the profit associated to some, generally speaking, vector x can be associated via the difference between revenue and cost. So as long as the outflow is less than the inflow in terms of, say, cash, then your profit is always going to be positive. And when revenue and cost are equal to each other, we usually call that the break-even point with respect to x. And of course, when revenue is less than cost, then we have a negative profit, or some people call it a loss. So we seek to maximize this particular functional or objective function, I guess you could view it as, with respect to these constraints and this restriction on our single variable x. Now, technically, we actually don't have any constraints because R and C are actually just components of our objective function. So if we actually construct our P of x via these R and C's, one can find that the P of x is just going to be equal to what? So it's going to be R, so 3.25x minus this quadratic function. So if we write that in descending order, that's going to be negative 0.03 x squared plus 3.1x minus 20, with the restriction that x must belong to the interval 0 to 80. So we seek to maximize this particular objective function with this particular restriction on x. So if we think about this from the graphic perspective, well, this is just a parabola, so we should know what that functional actually looks like. So we are going to have a vertical intercept of minus 20, so minus 20 is going to be located there, and we can find where the vertex of this parabola is via, so the x vertex is going to be equal to negative b divided by 2 times that leading coefficient. And one can find that that value is actually going to be associated to our maximum value. So this is going to be our x star, and our functional f is going to have this particular picture, and one can find that for this particular function, 80, which is the maximum number of donuts we're permitting to sell in a particular day, is actually going to be located there, and that's going to be a close point on both of those boundaries. So notice that for this particular functional, because it doesn't have to be a parabola, this point is going to be a maximum because, one, the slope of the tangent line at that particular point, so p prime of x star, is going to be equal to 0, and the function is going to be concave down at that particular point. Because remember, if p prime is equal to 0 and the function is concave up, then that point would then be a minimum or a local minimum for the curve at that point. Right? So our goal is to show that p prime of x star is equal to 0, or find the x star that makes that true, and then verify that p double prime of x star is actually going to be negative. That's going to imply that that is a local maximum. So keep in mind, for a closed bounded interval in terms of your domain, you don't just have to check the values for which the derivative is equal to 0. You also have to show or analyze the boundary of your functional as well. Because notice that 0, -20, and 80, whatever that height value is there, are going to be local minimums. So if our goal is to minimize profit, then those would be the points for which we would be interested in, where this right point would be a local minimum, and the point on the left would be a local and also global minimum for our projective, our profit function P. Right, so let's just analyze those particular values right quick. So P of 0 is actually going to be equal to -$20. That's obvious to see. And if you plug in 80 into our profit function, you can find that that's approximately equal to $36. So these are our endpoints. Those need to be constructed. So as long as we have a x value that generates a profit that is bigger than 36, provided that x is between 0 and 80, then that is going to be our ideal point. Right. So now that we have our profit function and we've analyzed our endpoints, now let us find all the points for which the derivative is equal to 0. So what we need to do is we need to differentiate this quadratic function, for example, via the power rule. So one can show that the derivative of our profit function with respect to x is going to be equal to what? So it's going to be that leading coefficient, -0.03 times 2, so that's going to be equal to -0.06 times x to the new power of 1, plus the derivative of 3.1x is going to be equal to 3.1, and the derivative of constants is just equal to 0. And our goal is to solve this equation for example, x0, and that's going to give us, for example, x star, or our potential x star. So once we solve that equation for x star, what do we have? So x star is going to be equal to -3.1 divided by -0.06, which of course is located at the vertex of that parabola, so it's going to give you the same number as before, and that's going to come out to approximately, what is that going to come out to? That's going to come out to approximately 51.67, which does belong to our interval 0 to 80. That's the only restriction that we have. Therefore, this value is feasible. Right? So once we plug in this x star into our profit function, we have that P of x star is going to be approximately equal to 60.08 in terms of profit. So we have a few profit functions for our extreme values. We have -20, 36, and 60, and those are the only feasible points for which a maximum does exist. -20 and 30 are minimums because locally you should be able to verify that those are indeed minimums, and we verified that this is an extreme point. Now, if you plug in P of x star into the second derivative, for example, the second derivative of the profit function is just going to be equal to -0.06, and notice that this is negative for all x, in particular x star. So that means this function is going to be concave down at this particular point. That means that is a maximum, a local maximum, and notice that it is the greatest of all maximums on that interval. In particular, there's only one maximum to consider, right? Because the other ones are both local minimums, with P of 0 being our global minimum, right? So since that is our only maximum to consider, that means 60.08 is the optimal profit for which we can get from selling donuts, where we need to sell exactly, or approximately 51.67, or somewhere around there like 50 to 52 or 51 to 52 donuts in order to maximize profit, right? So that's one example that just uses derivatives and also the power rule for optimizing profit. Suppose now that you have an ad that is 10 seconds long and you sample a series of individuals and you see pretty much or measure their attentiveness to that ad, where T ranges from, for example, 0 to the maximum of 10 seconds. And you model their attentiveness for all those individuals, you average them, and you propose that the model for the attentiveness for a randomly selected individual follows this particular curve. So if that is the case, at what point on average does a random person expect to have a maximum attentiveness to this particular ad? So if you don't know the graph of this, that's perfectly okay. We can approach it blindly, since generally speaking, once we hit multivariable functions, especially like 5D or 60, you won't be able to graph it anyway. So let's sort of trust the math here and see where we can go with it. So the first thing that we need to do is find all the extreme points, which is where the derivative of this function is equal to 0. So the first thing I'm going to do is find the derivative of t, which is going to be the derivative of the product of the functions t and minus 0.03 t squared. So we need to use the product rule here. So what I'm going to do is I'm going to do the first times the derivative of the second. So the derivative of an exponential is going to be e to the minus 0.03 t squared itself times the derivative of that interior function. So it's going to be negative 0.06 t. That's via the chain rule. So first times the derivative of second plus the second times the derivative of the first function, and the derivative of the first function is going to be t, so the derivative of that is going to be equal to 1. And what we can do here is then set this equation equal to 0, and that's going to give us our extreme points t, right? So we're going to set that equal to 0. Let's clean this up a bit also, because this is definitely a little bit messy. So what I want to do is I want to put that constant in front of that t here. So we're going to have negative 0.06 t e to the minus 0.03 t squared, and then we're going to have plus e to the minus 0.03 t squared is equal to 0. We have a greatest common factor of this exponential term. So for example, I can factor that out on the right hand side or the left hand side, but my coefficient is negative, so I'm going to keep it as so. So I'm going to have negative 0.06 t plus 1 times e to the minus 0.03 t squared is equal to 0. Now, how do I solve this equation for t? Let's first off analyze this exponential or Gaussian function. I guess you could view that as if you're familiar with such things. You should be able to show that the graph of that is going to sort of look something similar to this. It's going to sort of look like a bell curve. So keep in mind that this function is never going to be equal to 0 for all values t in the set of real numbers. So if I divide both sides by e to the minus 0.03 t squared, that's never equal to 0, provided that t is a real number, so we're not going to be losing anything when we divide by that. So if I divide both sides by e to the minus 0.03 t squared, what is that going to give me? So that's going to give me negative 0.06 t plus 1 is equal to 0, and then I can subtract 1 and divide by 0.06, so I'm going to have that is equal to what? Oh, and also don't forget about this t. Notice that we have a t there and we have a t there, so technically that should be a t squared, so let's not forget that. So we have negative 0.06 t squared, so t squared is going to be equal to 1 divided by 0.06. And then from there we can take the square root of both sides. So we have that t is going to be equal to plus or minus the square root of 1 divided by 0.06. And that's going to be equal to plus or minus the square root of 16.6 repeating. So that's going to give us two solutions, right? So the first solution for t is going to be equal to minus the square root of 16.6 repeated, and t2 is going to be equal to positive the square root of 16.6 repeating. Keep in mind that we have a restriction on t. In particular, t must belong to the interval 0 to 10. Notice that this t1 does not belong to that interval. That means that solution is not a feasible solution for our optimal value. Okay, now this does satisfy all the constraints, therefore that is our feasible solution. So once we actually take the square root of 16.6, we can find that our optimal value t star, possibly, is going to be approximately equal to 4.08 seconds. Right. Keep in mind we have not proven that this is a optimal for in terms of maximums for our solution, but it is definitely a feasible solution just since it does satisfy all of our restrictions. So if you take the second derivative of our attentiveness function with respect to t, i.e. the second derivative of at, one can find that that's going to be equal to e to the minus 0.03 t squared. So you have a few product rules and chain rules to do here. So 0.0036 t cubed minus 0.0018 t. So once you have that and you plug in this feasible solution, so a double prime of t star, that's going to come out to approximately negative 0.2971. So This t star is the value for which the derivative is equal to 0, so it's either maximum, minimum, or neither of them. But we've shown that the second derivative at that particular point is negative, which means the function is concave down. Therefore, since that is an extreme point and the function is concave down at that extreme point, that means we have that t star is a local maximum. And that is the only feasible solution. That is a local maximum. That means that is our true solution, provided that the endpoints aren't going to cause us any issues. So if we actually look at the graph of this function here, so the function a of t, you should be able to show that the graph is going to look similar to this, where this point here is 10, and this point here is our 16, or whatever the time was, 4.08 seconds. 4.08 seconds. And that's going to give us our curve, right? So that value, of course, is an attentiveness value of 0. And at the endpoint, one can show that the value of a of 10 is going to be equal to approximately 0.50, which is less than our attentiveness value at the extreme, which came out to what? What did that come out to? Let's see. So that's going to come out to approximately, so for that particular value, that's going to come out to approximately 2.48 attentiveness, whatever unit, like smiles or happiness or whatever, right? So since that is the only maximum, keep in mind blindly we should be able to ignore the graphs and still trust our values. So since 2.48 is greater than the other extreme values, because you can't test the second derivative at the endpoints because technically they don't exist there, you should be able to see that, okay, since that is the only maximum on our entire interval, it by default is going to work. But for example, if this curve happened to come up, you need to make sure that that y value for that local maximum is less than the value for which we found, because local maximums does not imply global maximums, but global maximums imply local maximums, which is the solution that we have. Also keep in mind for nonlinear curves, the optimal value need not be unique. For example, if you think about, for example, the sine function, which for example sort of looks like that, that would give us, for example, two solutions, if we look at it, for example, bounded interval, that are both going to give us optimal values. So keep in mind, optimal solutions are not unique if, for example, they have the same exact value for which we're trying to optimize. So just keep that in the back of your mind for general problems. The next problem, if you took already a single variable calculus course, probably is one of the more famous types of problems that you usually do when it comes to optimization with single variable calculus, and that's the cardboard box problem. So let's assume that we're working with a rectangular piece of cardboard that is of dimensions 15 feet by 12 feet. And what we plan to do is we plan to make a box out of this cardboard by cutting squares of equal size out of each of the corners and then folding those corners up to create the height of that box. So with a 15 foot by 12 foot piece of cardboard, what is the maximum possible volume of a box that you can actually make with these particular specifications? So what I usually like to do with problems that usually revolve around geometry is to draw a picture. So what we're starting with is a rectangular piece of cardboard, where the rectangular piece of cardboard is, by initialization, 15 feet by 12 feet. And what we're going to do is we're going to be cutting square corners out of each of these sides. So squares and squares, each of some unknown length, and we're going to call that length x. Okay? So each of those are x's. And what are we going to do? So the volume of the box is going to be equal to what? So this is what we get when we, for example, fold our edges up. So we're going to be folding this up, we're going to be folding that up, we're going to be folding that up, and we're going to be folding that up. So when we look at this from a three-dimensional perspective, and let's actually give these some names. For example, let's call this length L. Let's call this length W. So that means that's L. That's W. And this height is actually going to be the length of X. So that means the height is actually going to be X. So when we look at this from a three-dimensional standpoint, So here's our L and here's our W, and then we have our X, right? So that is our height, right? So there is our little ugly box, okay? So what is the volume of this box? So the volume is going to be equal to length times width times height, which is going to be equal to X. Okay, so keep in mind that what exactly is L? So L is going to be equal to, so we're going to be focusing on this dimension first. L is going to be equal to 15 minus 2x, and W is going to be equal to 12 minus 2x, right? That means we can represent the volume as a function of x. So that means volume is going to be equal to height times length times width, right? So we need to figure out the value of x that optimizes volume, okay? So notice that we have a couple restrictions here, right? Because notice that length and width must be greater than or equal to 0. Because if we make, for example, x to be equal to 200, both of these values are negative, right? So what is the restriction on x in this picture? So keep in mind, if L is greater than or equal to 0, that means 15 must be greater than or equal to 2x, which means that x must be less than or equal to 15 over 2, which is going to be 7.5. And if we mandate that width is greater than or equal to 0, that means that 12 is going to be greater than or equal to 2x, which means x must be less than or equal to 6. And both of these must satisfy, right? Because if x is equal to 7, that means that's too big for the width, but it's okay for the length. Therefore, it has to satisfy for both of them. So that means x must belong to the interval 0 to the minimum of 7.5 and 6, which means that x must belong to the interval 0 to 6. Or in inequality notation, 0 is less than or equal to x is less than or equal to 6. So that is our restriction for this particular restraint for which we seek to optimize. So now that we have our function, our objective function that we seek to maximize, and we have all of our restrictions in place, now we can use our calculus in order to solve. So the very first thing that I want to do, instead of doing some triple iterative product rule, is just expand that into a polynomial and then use the power rule directly. So once you do that and you don't make any mistakes after you combine like terms, you should be able to show that this volume function is in the form 4x cubed minus 54x squared plus 180x. Okay, and keep in mind we're assuming that x belongs to the interval 0 to 6, and our goal is to maximize v. So again, we want to set the derivative equal to 0, find all solutions, and find those points that are feasible that satisfy the constraint that the second derivative is negative. So using the power rule for v, we're going to have v prime is going to be equal to 12x squared. 54 times 2 is going to be 108x, and then the derivative of 180 is just going to be equal to 180. Right? So what we're going to do is we're going to set this equal to 0 and then solve. So that's going to give us a quadratic equation, which is going to be a little bit messy. So before I do that, I'm just going to go ahead and find the second derivative and see what that is. So that's going to give us 42x minus 108, because once we solve this equation for x in the v prime x is equal to 0 equation, then we're going to plug them into that equation and sort of see, is it positive or negative there? Okay, so once we use the quadratic equation on my v prime function, right, so we're going to use the quadratic equation unless you can factor that, which is a little bit messy. So x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay. Once you do all that product out, you're going to come out to 108 plus or minus the square root of, that's going to come out to 3024, all divided by 24, which actually does reduce. You can start, for example, with 4 and then go from there. So this is going to reduce to x is equal to 9 plus or minus the square root of 21 divided by 2. So we have two Potential solutions not counting the endpoints. So, for example, x1 is going to be equal to 9 minus the square root of 21 over 2, and x2 is going to be 9 plus the square root of 21 divided by 2. Okay, so keep in mind, what is the square root of 21? So the square root of 21 is strictly in between the square root of 25 and the square root of 16. So the square root of 21 is in between 4 and 5. Remember that we had a restriction on the value of x. Remember x must be between 0 and 6. So for example, if we add a number between 4 and 5 to 9, that's going to give us some number that is strictly bigger than 6. That means this value here is not feasible, right? But if we take a number from 4 to 5 and subtract that from 9, that's going to give us a number from 4 to 5, right? Which are going to be feasible in this particular problem, right? So in terms of the differential perspective, that is our only feasible solution. And then we can, of course, analyze the endpoints if we desire. Okay, so you should be able to show that once we plug in this particular x value into the second derivative, so if you show, or if you do, for example, v double prime of x1, this is going to be equal to 42 times 9 minus the square root of 21 divided by 2 minus 108. You should be able to show that that is actually going to be a negative number, and you can do some quick math to sort of analyze that for yourself. So that means this x1 is going to be a local maximum, but that doesn't mean that's going to be our global maximum on our feasible region. Right? So let's look at a graph and sort of analyze the endpoints and sort of compare these values out. So once we look at this particular picture, so our polynomial is going to look like what? So remember that v of x was equal to x times 15 minus 2x times 12 minus 2x. So we have a few x-intercepts here. So we have, for example, x is equal to 0, x is equal to 6 is going to be generated from that particular value, and 7.5 is going to be generated from that particular vector. It's a positive leading coefficient, therefore the graph of this function is going to look as so. Keep in mind, x must be belonging to the interval 0 to 6. That means this area here, blocked off in red, is infeasible. In particular, this was our x1 and that was our x2. So x2 was actually going to be a local minimum, but that's infeasible, so we don't need to consider it. And we should be able to show that our endpoints 0 to 6 are actually both going to be equal to 0. So the volume of 0 and the volume of 6 is actually equal to 0, which are going to be less than whatever value we get for that particular value at x1. Okay, so once we have that, which is approximately equal to 2.21, then we can find the maximum possible volume that we can get by substituting that into our equation. So the maximum possible volume is going to be approximately equal to 2.21 times 15 minus 2 times 2.21 times 12 minus 2 times 2.21. And what is that going to come out to? So that's going to come out to approximately 177.23 square feet. Okay, so that's the maximum approximate volume that you can obtain via a 15 by 12 foot piece of cardboard. Where keep in mind our 15 by 17 cardboard that we originally started with comes out to 255. So are you wasting a lot of cardboard when you cut out those little squares in the corner? You can make that judgment on your own, but based on the geometry and requirements here, 177 is the maximum volume that we can get out of that cardboard piece. So those are some of the applications that you can do for single variable calculus. Later on, we're going to be looking at numerical methods and multivariable methods for solving optimization problems for linear and nonlinear problems. So until then, I hope you take care. Thank you.